Hello and welcome to helpyourmath.com. In this video, we're going to look at simplifying radical expressions with numerical and variable radicand factors. Before we get started, just a few things to review. When is a radical expression in simplest form? For right now, we're going to base it off of this. N is the index, so the index that is the number that's wedged in between like the little checkmarky deal of the radical. If there is no index given, it's assumed to be 2, the square root. Okay, so index, it is when the radicand, that's the expression that's under the radical, this guy here, has no perfect power of n factors besides 1. So we shouldn't be able to pull out a perfect power of n that's a factor within that radicand. We're going to talk about how we identify if we do, in fact, have any of those perfect powers. For the numerical part, and I did do a video previously where I just look at numerical radicands, so if you need to review, please stop and go back to that video. But I'll go through a little bit of review here as well. So we're looking to find these perfect powers of n, and then what we would do is we're going to take whatever this numerical, so this is going to be a number, right? Let's just say it's, we're going to use variables here, I'm sorry. We're going to say it's a, but something we know is that a could be rewritten as b to the n times c. So we'll notice that b to the n, that is a perfect power of n. And what we do is we can then rewrite the radicand as this multiplication of two factors. And then we can split these up if we so desire. And at some point you get comfortable with these, you can kind of skip a few of these steps. I try to show them all, but again, when you get comfortable, start skipping by all means. And then the nth root of b to the n would be b. And I am making an assumption here that b is non-negative. So I do want to make that clarification, because if the index is even, we can't deal with these negative numbers. We would have no real root. So we're making the assumption that all the radicands we're looking at are in fact positive or non-negative. So that includes 0. And then we would just write, so b becomes, we take the nth root of b to the n, we just get a b. It now becomes the coefficient of this expression. And left under the radical was that other factor that now doesn't have any perfect powers of n. For the variable part of the radicand, we're going to look for the largest multiple of the index that's smaller than or equal to the exponent of the variable. And I'll do an example for this because I know I went very abstract with my numerical, but let's just say we have the cubed root of n to the 14th. Look for the largest multiple of the index, so the largest multiple of 3 that's less than or equal to 14. Well, that would be 12, because 3 times 4 equals 12. So we're going to rewrite, we're kind of like undoing the same base multiplication property here. We're going to rewrite n to the 14th as that multiple of the index, so n to the 12th, but this is supposed to be 14, so what plus 12 would give me 14? That would be 2. And then, just like we did up here, I'm going to just separate the perfect power of 3 from what's left. And now I can actually do this. And to simplify the variable part with the exponent, we divide the exponent by the index. 12 divided by 3 is 4. That becomes the exponent, and that is the cubed root. So the cubed root of n to the 12th is n to the 4th. N to the 4th becomes the coefficient, leaving behind this cubed root of n squared. And we want to make sure when we are dealing with radicals that aren't square roots, we're including the index each time. So notice each time I'm putting that index of 3. Okay, and one more thing. When is a radical expression in simplest form? So I addressed that already. What I wanted to show here was this table. So I went through this table in the previous presentation, so I'm just going to, spoiler alert, have those here. We have the x squareds here, so these are our perfect squares. These are the numbers we want to look for if we have a square root. And again, we might not see the number 16, but maybe 16 is a factor of the radicand that we're given. That's what we want to look for. And then this is called our perfect cube. Plural. These are the perfect cubes. If we have an index of 3, we want to see, is 8 a factor of the radicand? Is 125 a factor of the radicand? This list here is some of the perfect powers of 4. They don't get a special name. And then these would be the perfect powers of 5. So each time we do an example, I'll have the list handy so that we can reference back to it. Okay, in our first example, we have the square root. I know it's a square root because no index is given. It's assumed to be a 2. The square root of 84, x to the 5th, y to the 10th. Let's consult our handy list. We're looking for our perfect squares. I don't even need this one at all. And so we're looking in this column for one of these is hopefully a factor of 84. Maybe it's helpful to start with the bigger numbers because we are looking for the biggest factor. If there are multiple, so if 36 is a factor, 4 and 9 are also factors. 36 is the biggest, so that's the one we would use. But in this case, I think if we check this one, it's a no, it's a no, it's a no, it's a no. And when I say it's a no, that means we're doing 84 divided by 49, we get a decimal. 84 divided by 36, we get a decimal. We keep doing that, but finally we get to 4, and we figure out that 84 is 4 times 21. And we're going to rewrite 84 as 4, the perfect square, times the other factor that brings us back to 84. And I'm going to color code these so it's a little bit, hopefully it's a little bit more coherent as to what I'm working on at any specific time. X to the 5th is not a perfect square. In order for it to be a perfect square, it would need to be a multiple of 2, which are the even numbers, and 5 happens to be odd. So we break up x. Remember, we're going to undo that same base multiplication. We're going to write it as the largest multiple of 2, which would be 4, times the other factor would be 1. We don't have to put the x to the 1. We don't have to put the exponent. Just visually, now we can see it clearly goes back to being x to the 5th, so I like that. I include it here, but I'll take it away again in a minute. And then y to the 10th, well, 10 is even, so y to the 10th is a perfect square. So I'll just write it as y to the 10th for now. Right now I'm just kind of separating, so I have my perfect squares ready to go, and I have my leftovers ready to go or to do nothing with. And I'm just going to underline the perfect square. So we have the 4, the x to the 4th, and the y to the 10th. All of these we're actually going to take the square root of, and when we do take the square root, they become the coefficients of this radical. The square root of 4 is 2, so we're going to write 2. And then under the radical, what's left over? The 21. Next up, we have x to the 4th, the square root of x to the 4th. So what we're going to do is we're going to divide the exponent by the index. And that's why we chose to rewrite this so that it is a multiple of the index, because now we're going to divide and we shouldn't get a fraction or decimal. 4 divided by 2 is 2. So we end up being able to take the square root of x to the 4th, and it's x squared. The x to the 1st is going to stay under the radical. And again, as I mentioned before, I'll drop the 1. Y to the 10th, just like we did with x to the 4th, we're going to divide the exponent 10 by the index 2. 10 divided by 2 is 5. Because we were able to actually divide or simplify, take the square root, we'll put it out in front. And just to put this as one solid color, our final answer here is 2x squared y to the 5th times the square root of 21x. And this is as simplified as this radical expression can get. Up next, we're looking at a cubed root. So we have the cubed root of 24 times a cubed times b squared times c to the 5th. And we're going to want to consult that list of perfect cubes. Here's our list of perfect cubes. We only have one number to check because 27 is already bigger than 24 and we don't check 1. So either 8 goes into 24 or we don't have to simplify the 24 because it doesn't have any perfect cube factors. Good news for us, 8 does go into 24 because 24 is 8 times 3. We're going to rewrite this, and just make sure when you rewrite, you're always including the index. We never just write a root because then you're turning it into a square root and that's mathematically unsound. So keep the consistency, keep writing that index of 3. I'm going to put my perfect cube and the other thing. And then for a cubed, well, it turns out the exponent 3 is a multiple of the index 3. So I'm in luck here. I don't need to do anything. It's all ready to be the cubed root of. B squared is too small. It doesn't even get as big as 3. So we're not going to be able to simplify it at all. We're just going to leave it b squared. And c to the 5th, so 5 is bigger than 3. So we will find a perfect cube factor in c to the 5th. And it's going to be, we're going to rewrite it as c cubed, because that's the largest multiple of 3 that's less than 5. And to get back to 5, I have 3 of them. I need 2 more, so I'm going to write it as c squared. And then just to highlight our perfect cubes, we have the 8, the a cubed, and the c cubed. So those are all the ones that we're actually able to take the cubed root of. The cubed root of 8 is 2. So we're going to put a 2 in front of the radical. I'll go ahead and set up my cube root. A 3 goes under the radical, the other factor. The cubed root, oh, my blue turned green when I highlighted it in yellow, but the cubed root of a cubed would just be a. The b squared just stays under the radical. We can't do the operation there, so we'll just leave it under the radical. The cubed root of c cubed would be c, and then we have a factor of c squared under the radical. And then just writing this so it's all one color, we have 2ac times the cubed root of 3b squared c squared. And that's as simplified as this expression can get. So I'll put a box around it. Now we'll notice in this example, the radicand is the same as the radicand in the last example. What's different? That's right, you said it, I heard it. The index is different. This one we don't see an index, so it's meant to be an index of 2. We're looking to find perfect squares. Let's bring up that list of perfect squares. I only need this column because 24 is already smaller than a lot of these. We don't even have to check any of those. 16 is a no. There is a remainder. 9 is a remainder. 4. We have a winner. Woo! So we're going to rewrite 24 as 4 times 6 because 24 is 4 times 6. A cubed is not a perfect square because 3 is odd, but it does have a perfect square factor. We would rewrite a cubed. We're going to break it down into a perfect square, a squared, times a to the first. B squared, hey, it's a perfect square. So we're just going to keep it b squared because we'll be able to take the square root of b squared. C to the fifth is not a perfect square because the exponent is odd, but we'll rewrite it as a product of the largest even number less than 5, which would be 4, times c to the first. And I think I mentioned this before, and I just want to shout out here to the square root. We are assuming that a, b, and c are all non-negative. So my disclaimer is that a, b, and c are greater than or equal to 0. This is just so it does mathematically make sense. So that's my disclaimer halfway through the problem. Perfect. And now I'm going to highlight my perfect squares. So 4 was a perfect square, a squared, b squared, and c to the fourth. Let's get rooting. The square root of 4 is right over here. I see it, 2. So we're going to say 2, and then under the radical, we'll still have a factor of 6. The square root of a squared is a, and then there's that other factor of a still under the radical. So this one went here, and this one goes here. The square root of b squared is b, and there's no factors of b left under the radical. And the square root of c to the fourth, 4 divided by 2 is 2, so we get a c squared in front of the radical, and then this c comes down and stays under the radical. So that's where these went to, came from, whatever the case may be. Writing it in one solid color, we have 2ab squared times the square root of 6 times a times c. Exampled out yet? I hope not, because I have some other ones. Now, for these last few examples, I did put coefficients that already exist. When we do take in this case, the fourth root of whatever we can take the fourth root of, they're going to join the coefficients that's already there via multiplication. So whatever comes out of the radical and becomes the coefficient will join the coefficient that's there, and we will multiply whatever we can multiply. So the numbers will multiply together, we'll combine the variables using that same base multiplication property that we keep talking about. And again, I'll try to color code everything, so hopefully we don't get confused because sometimes we end up with like multiple 2s, and it's like, wait, was that 2 from there or from there? I know. So I'll color code it. Hopefully it'll make more sense. I want this because those are my perfect powers of 4. I'm going to just go ahead and start by writing the 2n, because we don't have to do anything with that until something else comes out of the radical. So that's just going to be there, and then things might join it. And now we're going to look for our perfect fourth powers of 4 of the radicand. I highlighted the 324 just because I'm going to use red for the the breakdown of it, and I want to be aware of what happened. Okay, so 324, we don't have to check 5 for a number of reasons. We don't need to check 256 because if we double 256, we're already over 324. Maybe 81. So does 81 go into 324? I don't know off the top of my head. Let's see. If it did, it would be times 4. And we get, it does! So 324 is 81 times 4. And that's what we want to use because we're looking for that perfect power of 4. I'm going to rewrite 324 as 81 times 4. Next up, we have m to the 14th. M to the 14th, 14 is not a multiple of 4. So notice my switch in language. I went from power to multiple because we're talking about the exponent here. 14 is not a multiple of 4, but it does contain a multiple of 4. The largest multiple of 4 that's less than 14 is 12. So we'll rewrite this as m to the 12th. That gives me 12 of my m's. I still need 2 more that are my not perfect power of 4. N to the 8th, well, 8 is a multiple of 4. So I'm just going to leave this as n to the 8th. And once again, I'm just going to bring down this coefficient for now. But now I'm going to space out my 4th power. And now I'm going to start looking for those perfect powers of 4. And again, I'll highlight them so they're very visible. 81 was a perfect power of 4, m to the 12th, and n to the 8th. The 4th root of 81 is 3. So we're going to put a 3 out here in front, joining the 2n that's already there, again using multiplication, and the 4 will stay under the radical. The 4th root of m to the 12th, we're going to divide 12 by 4. We get m cubed. And m squared stays under the radical. And n to the 8th, well, 8 divided by 4 is 2. So the 4th root of n to the 8th will be n squared. Now what we're going to do is we're going to multiply samesies. So I'm going to multiply the 2 times the 3 because they're both numerical factors. And I'll multiply the n by the n squared because they're both base n factors. And I'll switch to one color because I think I already made this plenty colorful. 2 times 3, so again, this is multiplication, that's 6. I'm going to put the m first just because alphabetically m comes before n. And now I have 1n multiplied by 2 more n's. That gives me a total of 3 factors of n. So I have 6m cubed, n cubed, times the 4th root of 4m squared. And that would be our simplified answer for this example. In another example, now we're seeing even more work to be done here. We have an index of 5, so we need very, very small table here. And before I get started looking, breaking down there's only one I even need to check because there's only one that fits in between 1 and 96, and that would be 32. But before I do that, I'm just going to bring this down because for right now, while we're simplifying the radical, we don't do anything with this. And then we have this 5th root. To make it abundantly clear, I'm breaking down the 96. And so 32 better go into 96. 96 is 32 times 3. It works. Whew, that's good. I mean, it's fine if it doesn't. We just wouldn't be able to simplify it, which is kind of like not very interesting. Next up, a to the 7th. A to the 7th is not a perfect power of 5, but it does contain a perfect power of 5 factor. In fact, it would be a to the 5th is the largest multiple of 5 we can get under the 7. And we need 2 more factors to complete our a to the 7th. B to the 11th is also not a perfect power of 5, but it also contains a perfect power of 5 factor. The largest multiple of 5 that's less than 11 would be 10, so we're going to write this as b to the 10th times b to the 1st. And now we're going to start taking perfect powers of 5, or root 5s. We're going to be able to take the 5th root of 32, a to the 5th, and b to the 10th. But before I do that, we're just going to write what's already in front of the radical, negative 5a squared b cubed. I'll go ahead and make some space there, but put my radical with my index of 5. And here we go. The 5th root of 32 is 2, so a 2 is going to join the coefficients. Left behind is that factor of 3. Then in terms of the base a to the 5th has a 5th root of a, and we have this a squared left behind. And b to the 10th has a 5th root of b squared because 10 divided by 5 is 2, and we have this single b left under the radical. And now we have multiple factors in front of the radical. We're going to multiply the numerical factors. We're going to multiply the base A factors. And we're going to multiply the base B factors. -5 times 2 is -10. A squared times A, that same base multiplication, add the exponents, is A cubed. B cubed times B squared, add the exponents, we get B to the 5th. And we shouldn't be able to do anything else under the radical. We're just going to rewrite it, 5th root of 3A squared B. And then just because I know I just did like pastel colors, I'll rewrite it. So our final answer is -10 A cubed B to the 5th times the 5th root of 3A squared B. And that is my final answer. These have been examples of simplifying radical expressions with both numerical and variable radicands. Thank you for stopping by.